Growing up as I did in the American Southwest, I spent a lot of time out of doors, walking to and from school or playing in city parks. It became second nature for me to observe the natural world, and for such a person as me, living in the Southwest, the sun was always a prominent part of the outdoor experience. Lately, I've begun to notice the shadows projected by the sun as I make my morning walks around my neighborhood. Especially in the winter months when the sun angle is low to the south, the barren tree branches project their skeleton-like shadows across roads and upon walls of houses, a puppet theater-like display animated by the cold breeze, as barren branches like bony skeleton hands grasp for life in the dead of winter. The effect of tree shadows projected upon sidewalk and walls makes me think of how pinhole cameras work, ray tracing light waves from sol to surface, bullet-like projections from 93 million miles away that yet seem so familiar to us as warmth upon cold winter face. Tree shadows possess a sometimes ghostly, ephemeral hint of some former solid substance, yet at other times are sharply defined, razor-like edges crisply defined in the harsh New Mexico light. During my walks, I began to think upon these shadows and marvel at the overlay of both crisp and ephemeral tendrils of shadows upon the very same surface. Their combined effect seemed more than the sum of their parts, almost three-dimensional in effect, resembling to me how camera lenses can render some objects sharply defined and others blurry and indistinct, all at the same time. It appears I was observing a similar effect with shadows projected by the sun, and I wanted to find out why. Photographic study seemed the most obvious way to start. I'd walk out with camera in hand or strapped around my neck, and soon the early sun's effect would be seen projected across street and upon house fronts. I began to notice that shadows close to their source appeared sharp and distinct, while shadows projected a long distance seemed much less distinct. I began to look for compositions where shadows from both near and far were projected together upon the same surface, juxtaposed like laboratory specimens awaiting dissection. Reading up a bit on how the sun's disk affects the moon's shadow during a solar eclipse, I realized it was due to the sun not being a point source of light like a pinhole, but as a disk of light with an angular size of 0.53 degrees. It has a main shadow called the umbra and a feathery outer shadow's edge called the penumbra. Umbra and penumbra, these were the very ideas I was looking for. Okay, this is a diagram of a tree. The brown circle, you're looking down from above, a tree outside, and to the right of it is the sun at 93 million miles away, and the tree has its shadow being cast upon a wall here, represented by this rectangle on the left. So the main part of the shadow of the tree is called the umbra, and there's also, though, this outer edge of the shadow called the penumbra, and we have the penumbra because the sun is not a point source of light. It's actually a disk, and it has an angular size of about 0.53 degrees. So if you're standing in the umbra of the shadow of the tree, you won't see the sun at all, but if you're standing in the penumbra, you'll see a portion of the sun's disk. So if you have a vertical surface like a wall or a building right next to the tree, very close to it, you'll see that the shadow of the tree is mostly composed of the umbra, the dark center portion of the shadow here, and that the fuzzy edges of the penumbra are not very prominent. They're just out on the edges of the shadow. But then if you move out to a further distance, if the shadow of the tree is projected a further distance away, you'll see that the main part of the shadow, the umbra, is much less wide. It's narrower. It's just this narrow zone in the middle of the shadow. And the penumbra, the lighter, fuzzier parts of the shadow out on the edge, becomes more prominent. And then as we move even further away, you'll notice that there's a certain distance we get. It's called the penumbral merge distance, or PMD. There's a certain distance where we lose the umbra, the main shadow, altogether, and wherever we stand, we're going to be seeing in the penumbra part of the sun's disk. And when you're in this zone or further out, the shadow is much less prominent and it's not as dark as it would have been when you're in the umbra itself. So the sun's disk has an angular size of 0.53 degrees, and that's the angle of view of the umbra of the shadow, as you can see here in the middle. It's also the same angle of the penumbras. The penumbras also spread outwards behind the object at a 0.53 degree angle of view. So because of that, we can actually calculate what the penumbral merge distance is. And so this circle on the right side is just the cross-section of the tree. It has a certain width, and half of that width is the radius, or r. And this 0.5 degrees is the sun's angular size, and half of that angle, this angle A up here, is this angle right here, and this forms a triangle, angle A, side R, and this PMD. So it's a real simple high school trig tangent function, and you can pause the video and go through that if you want to, but basically it comes out to the width of the tree times 108.1 is the distance at which the two penumbral shadows merge together. So 108 times the width of the object. So here is an example of two objects that are different sizes, different widths, and they're the same distance from the wall that the shadow is being projected upon. You can see the narrower object, because of its narrower size, this distance is already at its penumbral merge distance in this example. But the wider object down here, it still has plenty of umbra. The main part of the shadow is still very prominent, and the reason why, of course, is it's a wider object. Its penumbral merge distance is 108 times its width, which is going to be a lot further of a distance than this narrower object. So this is one example that we see in some of these photographs, is two objects at roughly the same distance from the wall, but because of their different sizes, the shadows have different properties. Here's another example, though, of two objects of the same size at different distances from the wall. So the top object is much closer to the wall. Its shadow is going to be sharper. You can see the umbra is much more prominent in the middle of the shadow, the penumbra not as much. But this further out object, it's the same size, but because it's further away, now I've shown it at the penumbral merge distance, and you can see the shadow on the wall is going to be much fuzzier and indistinct. And we've seen photographs of these examples here of two trees, very similar in size, but two different distances away from a house, and the shadows look very different. Though we see with light, it itself is invisible unless reflected or scattered. Invisible light becomes visible when interrupted by some object solid enough to obstruct it by means of its shadow. Shadows both hide the light and reveal to us the nature of its source simultaneously. Through the cinema-like play of shadows upon some reflective screen-like surface, we see the world revealed to us as if through a glass darkly.